Today, I'm going to teach you how to build Connect4 in the terminal using Rust. I recently took on the challenge of learning Rust, and in a bid to get my hands dirty and consolidate my own knowledge, I thought about building a game of Connect4. I think it's a good task for people new to the language because it's simple enough that you can do it in a single afternoon, but complex enough that you need to explore a lot of features of the language in order to get something good. On the screen right now, you can see exactly what we're going to be building, so without further ado, let's get into it. Okay, let's make a new directory, Rust Connect 4 tutorial, and let's open it up in VS Code. Let's start a new Rust project with cargo init. And this is a no dependency project. We won't need any dependencies for this, so we can head into our source /main rs file and get going. Oh, and before we get into it, I'll show you what Rust version I'm on. And cargo. I'm just going to rearrange VS Code so that we can have a terminal on the right because it'll be easier to see our board when we eventually start playing. In Rust, the best way to get started is often by defining our data structures, so let's start by doing that. Typically, a Connect4 board is 7 slots wide and 6 slots tall, so we can store these integers as constants. Const board width. We'll use an uSize type, as we'll be working with vectors, equals 7. And const board height equals 6. We can use the constants above to define a board type. This is going to be a 2-dimensional array representing the rows and the columns. So type board equals, and each of our slots on the board is going to be represented by a small integer for the player. So I'm thinking 0, 1, or 2. So this can be represented by U8. And the rows are going to have a length of the board width. That's how many items we expect in this particular vector. And the columns are going to have 6 slots for the board height. So next we want to define our player type. And this is what this U8 is going to represent. So let's have enum player. And I'll have a player 1 represented by 1, 2 by 2. And it's also going to be useful to us to have a none type, which we can represent with 0. We'll get on to why that's useful in just a second. But while we're here, let's add some attributes to this enum. So first, I want to be able to clone and copy it and print to log. And it'll also be useful to have a partial equality check on this enum. And we want our integers to be unsigned 8-bit integers. So we can add rep r u8. And finally, our other important data structure is the game itself. Let's create a new struct called game. And we're going to want to have the current move, the current player. We want a representation of the board. We want to know if the game is finished. And we also want to store, if there's a winner, who that winner is. We'll start with the current move. Now, the maximum number of moves is going to be 6 times 7, which is 42. So that can fit in an unsigned 8-bit integer. Current player, let's represent with our player enum. Board can be our board type. Is finished, which is simply a Boolean. And the winner will also be a player. And already we're seeing the use of our none player because games of Connect4 can end in a draw. Next, I want to implement this game data structure with an initial state. So if we implement game and we have a default function, returns the game, here we can specify that the current move will start as 0. The first player will be player 1. Yeah. 1. Now for the board, we could calculate this dynamically, but I think it's more useful as a visual aid to actually see the 2D array. So I'm going to spell it out with zeros at first. I think while we're coding, it's useful to see the board in front of us. So each row has 7 slots. 1, 2, 3, 4, 5, 6, 7. And there are 1, 2, 3, 4, 5, 6 rows. Is finished will be false. And the winner we will define as player none. To prove my point about why I want the board this way, let's say we replaced all these zeros with player none. Suddenly, we lose the ability to easily see what's going on at a glance. Let's put that back. But the trade-off of this decision is that we're going to need a way to convert from an integer to a player type. And we can do that by implementing the player and adding a fromInt function. So under player, we will implement it and add this function fromInt that takes a U8 integer and returns a player. And we'll use a match for this. So match int 1 goes to player 1, 2 goes to player 2, and anything else goes to player none. Okay, these are all the types that we'll need, so we can actually get on with visualizing the board now. For debugging purposes and for the game itself, we're going to want a nice way to print the board to the terminal. So let's work on that now. I want to put some colors into the terminal, and probably the normal way of doing this is by using a crate. Instead, I'm going to use hexadecimal escape strings because that way we can keep this project as 0 dependencies. You only need Rust to play this game. I'm going to copy these escape strings in and put them with my constants at the top. Orange for an orangey yellow color, red for red, and reset to set the color back to normal. Now if we jump down to our game, we can implement a function to display the board. So function display board takes an argument of the game. Then I'm going to copy in some characters that make it very clear. We'll have connect for and the move number at the start. And I'll just print a line of dashes in the middle and a line of dashes in the end. So between these two, we are going to show the winner. And up here, we are going to show the board. Okay, to print the board, we're going to map through each row and use an emoji to symbolize each player's piece or an empty slot. So for row in self board, let's define a string version. So take the row and we will make it iterable. We are going to map through each cell, which we will borrow. And we will perform a match on the cell. So if it is 1, we'll return red, 2, we'll return yellow, and anything else we will return black. Then let's collect those results into a vector of borrowed string types. Call that. And finally, we'll join everything so that it's all on one string. And I was just missing a dot there. Now let's put in the emojis for our pieces. And now we can print that line. So print line macro. This will be the row string. And while we're here, let's also do some code to eventually print the winner. So if the game is finished, if self is finished, then we will match against whoever the winner is. So if it is player 1, then we will print to the console and we'll say player 1 has won. And I will color this orange. Likewise with player 2. And then if no player is the winner, we will declare it's a draw. Just a bit of cleanup. We can finally start to see something in our terminal. So let's go down to the main function. We can get rid of this. And let's create a game. I know we're going to have to change the game state, so this will be mutable. Let mute game equal a game, and we'll run the default function, and then we'll run game display board. And if I head over into my terminal, now run cargo watch. I like to use this version of the cargo watch command. The C flag clears the terminal between each change. The W flag tells cargo watch to watch what's in the source folder. And the X flag with run tells us that we only want to run when there's a change. All right, we're getting a few warnings because we've got a few unused variables and fields, but there is our connect 4 board on move 0. We can now start to make functions like a play move function and see that it actually does what we're intending. All right, back in game, I'm going to close this display board function and we will write a play move function. All right, so this is going to need to change the game state. So our first argument will be the game, but there'll be a mutable version. So we'll use an ampersand to borrow and mute to declare that we want to be changing the game. Self column, because we're working with vectors, I will use uSize. When a connect 4 piece is played, gravity takes it to the bottom of the board. So we need to fill up our columns from the bottom up. So here's one way of doing that. If we use an if let sum row and we create a range from 0 to the height of the board, then because we need it to start from the bottom, we can reverse this range, dot reverse, and then we'll find the first item in that range starting at the bottom where there's a 0. And if we find a 0, we can play a piece. Find a row. We know the column. We're going through the rows. Self.board. Row comes first, then column. And we want to know if it equals 0. So what this piece of code does is it takes the column that the player has chosen. So it starts at the row that has the highest index and looks for 0. If it doesn't find it, it keeps going up until it finds a 0. And if it finds a 0, then we want to play a move. Okay, so if we open up curly braces, then we can change the current slot with self board row and then column. We're going to change that to the current player. This will be a uSize, so we need to say as U8. We want to increment the move, so self current move plus equals 1. And then we want to change the player. So self current player, we'll use a match depending on what the current player is. If it's player 1, change it to player 2. Otherwise, the default is that the player is player 1. So let's play some moves and see if they show up. Game, play move, and we'll say player 1 chooses column 3. And there it is. Let's say all the players choose column 3. Nice. Let's try 1, 2, 3, 4, 3, 2. Player 1, player 2, player 1, player 2, player 1, player 2. Looks like it's working. Great. But there is a problem. If I take this first move and run it more times than there are slots in that particular column, well, the game state has maxed out at 6 moves for this column. There's nothing telling the user why they can't choose this column again. But there's nothing to tell the user that they can't choose this column again. So we need to introduce some kind of error handling in our code. So we go back up to where we implement our player enum I'm going to introduce the concept of a move error, and that's going to be another enum. So enum move error. The error we've just spoken about is that the column is full, so we'll call that column full. But there are a couple of other scenarios where the user won't be able to take a turn. One of them is that they've chosen an invalid column that's outside the allowed range. So we'll create invalid column. And of course, you can't play a move if the game is over. So we'll have game finished. And let me implement the debug attribute, derive debug. As this is a terminal game, we're going to want our errors to be printed to the terminal. So we're going to want to implement the standard format display type for move error. And then we can create a format function that prints the errors in a way that we want. So we will implement standard format display for the move error enum. And then inside that, we'll have a function fmt for format that takes itself, and then an argument f, which is borrowed, it's mutable, and it has a type of standard formatter. It expects this lifetime, and it returns a type of standard format result. Okay, and once again, we can handle this with a match. So if we get a move error of type column full, then let's use the write macro and we will show the error and we will say column is full. The invalid column, we'll say column must be between 1 and 7. And finally, when the game is finished, we will write the error and game is already finished. And I've just noticed that for this lifetime type, I used dash instead of an apostrophe, and now the compiler is happy. So if we return to our play move function, we can now handle these errors. So if the game is finished, then we'll return an error of type move error game finished. And if the column is outside the board, if the column is greater than or equal to board width, then we will return a invalid column error. Because we're using unsigned integers, we don't need to check if the integer is below 0 because that's going to be caught by the compiler for us. So we only need to check if it's greater than the board width. And here, if our if condition is not met, we can say else, and we'll return an error. Move error column full. And we need to delete one curly brace. The compiler is not happy because we haven't specified our return type. So let's return a type of result, which is either void or it is a move error. And that means we just need to go to the bottom and return an empty OK and one semicolon. So this returns the errors, but it doesn't print them. For that, we can create a small display error function. So we'll say display error, and this will take the error as a string. We'll display the board in the error state, and we'll print an error, make it red. So I'll have those curly braces for the red color error, and then 2 more. So it's red, and the second curly braces, that will contain the error, and that will reset the color back to normal. We've got to a point where it would be very useful to calculate if the game is won. Now, this was a bit of a challenge and it took me a few tries to get a function I was happy with. We need to calculate 4 slots in a row that can be either vertically in a row, horizontally, or diagonally. And there are 2 types of diagonals we need to account for. There's a top to bottom left to right diagonal, and there's a bottom to top left to right diagonal. So I will start a new function, calculate winner. And again, this has to change the game state. So we will have an argument that's mutable. We want to return the player that has won, or player none if there is no winner. So to represent the possible directions that you can get a connect for, I'm going to use an array of tuples. So let directions equal an array. So for a horizontal connect for, we're not going to increment the y-axis, so that will be 0, but we are going to increment the x-axis. So we'll say 1, this direction is horizontal. For vertical, it's the other way around, so we increment the y-axis, but not the x, so that is vertical. Then we've got our diagonal types. The first diagonal type starts at the top left, and then goes to the bottom right. So we can say that we increment both the x and the y-axis in the same direction. Top left to bottom right. And then the other diagonal starts in the bottom left and goes up to the top right. This has a negative increment on the y-axis, -1, and a positive increment on the x. If that seems a bit abstract, when we start writing the function, we'll see how this directions array is going to help us. Also, if it seems weird that the y-axis is coming before the x-axis, if you're wondering why we're putting the y-axis before the x-axis, that's because we're working with a 2D array, and by its nature, the outer array or the row is on the y-axis, and the inner array or the column is the x. I'm going to take a brute force approach where we go through every slot and check every direction. So for a row in the range 0 to the height of the board, and then we'll have an inner loop for a column in the range 0 to the board width. This will cover all the slots. In terms of compute complexity, this is an O of n squared algorithm, and we will let cell equal that exact row and column. If the cell has a value of 0, we can skip it. Most likely, a lot of cells are going to be able to be skipped. But if the cell is not 0, I'm going to move our directions to the top. And then we need one further loop to go through each of these 4 directions. In directions, to keep the compiler happy, I will return the default winner, which is no one, player none. Now we need to write the algorithm or logic that actually traverses each of the directions and tells us if we have a winner. So first I'm going to declare a consecutive count, and we know that if that reaches 4, then we have a winner. Let's int consecutive count equal 1. And then we'll need to keep a record of the row and column of the traversal. As we already have a row and a column going around, we'll use R and C. So let mutable R equal row, and we'll add the row step. I'm getting an error because we've got 2 conflicting types, so we can declare the row as assigned size integer, and we'll do the same for the column. C equals col as size plus col step. We enter a further loop. Right, for as long as the row is greater than or equal to 0, and the row is less than the board as size, and the column is greater than or equal to 0, and it's less than the board width as size. This means that we have traversed onto a valid slot. Now we need to see what the value of the cell is that we've traversed to and whether it's the same as our starting cell. So if this cell, which we can get by using R now as U size and C as U size, that equals the value of our starting cell, then we can increment the consecutive count. And if that increment takes the consecutive count to 4, then we have a winner. So if the consecutive count equals 4, then we'll say that the game is finished. and we'll return the player. Right now, we have an integer value, but we thought of this in advance and we can use our player from int function and pass in the starting cell. Now, if the slot we've traversed to is not the same as our starting cell, then we want to break the loop, as there's no point traversing further in this direction. So else break. And if the loop is not broken, we can increment our rows and columns in the direction specified in our direction array. So r plus equals whatever the row step is, and likewise for c, we can add on to it whatever the call step is. So hopefully our directions make sense now. For example, for the horizontal direction, we're just going to be incrementing the column step. For the vertical one, we'll just be incrementing the row step, and so on. Finally, a couple of small optimizations to save us performing calculations that we don't need. If we know that under 7 moves have been played, then numerically there cannot be a winner. At least 7 moves need to be played for the first player to win. If the current move is less than 7, then shortcut to return player none. The entire Connect 4 board can be filled with pieces and there may still be no winner. In that case, it's a draw, and we also need to handle that. Right before the final line, we can say if the current move is equal to or greater than board height as a U8 times the board width, then we can also set the game to be finished. And we'll return the winner as none. We can then use this function inside our play move function. Let's move the move increment up into this if statement, because you can only make a move if you hit a valid slot. And then after that logic runs, we can try and calculate the winner. So let's create a new variable, calculated winner equals calculate winner. If that function actually returns a player, so if calculated winner does not equal player none, then we can declare the winner. Self winner equals the calculated winner. Otherwise, we can change the current player. So this is the final piece of our Connect 4 game engine, and all that's left is to get the inputs from our users. To get those inputs, we're going to use the standard IO crate that comes with Rust. So right at the top, we will use standard IO. We'll go down to main. So as long as the game hasn't finished, then a user can submit a move. So we'll say, while the game is not finished, and I'll print a new line. We'll also print the player whose move it is. So let's match against the current player. If it's player 1, we'll print player 1. Likewise, player 2. And by default, we will return nothing. As you can see, my terminal is going a bit crazy, so I'm just going to stop that while we write this loop. We also need to prompt the user to enter a column. So let's say enter column between 1 and 7. We'll define a new variable for the user's move. So let mute user move equal a new string. And now we'll call the standard input function from the IO crate. And this will actually get an input from the user. So we want to read the line and put it into the user move. Mutable user move. For good practice, if that doesn't work, I'll have an error message, failed to read line. Next, we want to turn our user move into an integer that we can actually use. And we'll need to handle if the input contains something unexpected, like a letter, or if it contains spaces, we can trim those out. So we'll let user move. This time it is an unsigned integer. And we will match the user move once it's been trimmed and also passed into an integer. If this pass isn't successful, we can handle that by displaying an error using our game display error function, and we'll send the error as a string, and then we can continue with the loop. And if the pass is successful, we get a number. We want to check this number is within our expectations. I'm also imagining that maybe, possibly, the end user of this game might not be somebody who's interested in programming, and it might be more normal for them to count from 1 instead of 0. So for our inputs, we'll expect 1 as the lowest value, not 0, and we'll count up accordingly. So if the number is below 1, or if it's higher than, then we will display another error. And this one is a move error of type invalid column. And we need to stringify that. And we can also then continue the loop. Otherwise, we'll return none. So presuming that we have now passed the user's move successfully, we now have an integer that we can actually play. So let's match game.playMove with an argument of user move -1. The -1 here is converting our user's move back to a 0 index system that we can work with. And if the move plays successfully, then we'll simply display the game state, game display board. Otherwise, in the case of an error, we'll display the error. And we'll pass in whatever the error is as a string. On the compiler just to check that it's happy. Nice. There aren't any warnings and we're almost finished, but there's just one more thing that I'd like to add here. And that's the ability to play multiple games. It's going to be a bit jarring if we have to stop the program every time we want to play a new game, so I think that's an important feature and it won't take too much effort to add. So I'm just going to hide this while loop because that code is going to remain exactly the same. And we'll wrap it in a parent loop that loops around once per game. This time we'll use the loop keyword. We're going to tell our user that they can press R to restart or Q to quit the game. Then we'll collect the user's input in a very similar way to before, but this time it's even simpler because it starts as a string and remains as one. So let user input equal a new string. Then we'll use the standard input function. We'll read the line using a borrowed mutable user input and add an expect. Just head up here and mark this input as mutable. And finally, we'll match a trimmed version of the user input. And if it's either capital or lowercase r, so we can say the game equals the game at its default starting state, and we'll run the displayBoard function. Or if the user passes an upper or lowercase q, then we'll simply print quitting, and we can break from this loop. And if the input is anything else, display an error of invalid input. And we'll stringify that. Missing one semicolon here. Okay, looks good. As a final touch, we can use an ASCII escape code to clear the terminal between turns, which will just keep things a little bit cleaner for our end users. So just above display board, I'll add a clear screen function. We will then print this escape sequence that I've copied that will clear our terminal. We can call this function right at the top of display board. And as you can see, all the extra compiler information disappears when I save. And we're just left with the board. And that's a wrap. All that's left is to play our game. It was surprisingly mentally taxing trying to beat myself, and I think I missed a winning opportunity a couple of times. But we can see at least that the game has worked. Player 2 has won. If we press R, we have a new game. So that's all for today. If you've been following along and you'd like to take the project further, you could maybe try to keep track of the victories between multiple games, or maybe you could turn this project into an HTTP server where a web client could use the game engine that we've created. I'm still fairly early in my own Rust journey, so if you have any critiques or ideas about how to write the application better, using more idiomatic Rust maybe, then I'd love to read your thoughts in the comments. Thanks so much for watching, and see you in the next one.